Welcome back, guys. We are going to do some more logic puzzles on the Brilliant app. So next up we have truth tables. Alice, Bob, Charlie and David have all been invited to a party. Charlie says that he'll go to the party if and only if Alice and Bob are going to the party. David says that he'll go to the party if and only if Alice or Bob is going to the party. So Alice and Bob, Alice or Bob. Alice decides to go to the party, but Bob decides not to go. Which statement is true? So Alice goes, Bob doesn't. So Charlie doesn't go, David does go. So Charlie and David, Charlie does not, but David does. It's got to be that one. A statement like Alice and Bob are going to the party is a complex statement made up of smaller statements. Alice is going to the party and Bob is going to the party. We can chart the relationships on a truth table. Each row of this table shows a different combination of statements. Right, yeah. So basically, or in this particular sense is the traditional or and not the mathematical or logical, because that would mean and or. In this does not necessarily mean that that rules that particular definition out, because this is not and Bob, so we don't actually know if this particular or is an and or a traditional or. Maybe we'll find out here. We can chart the relationships on a truth table. Each row of this table shows a different combination of statements that may be true, denoted by a 1, or false, denoted by a 0. Once we have filled in some smaller statements on the table, we can combine them to form complex statements. We can shorten this using... I'll try again. We can shorten this using some notation. Up means and, down means or, and sideways L, or whatever you want to call it, means not. So, surprisingly, these three symbols are enough to represent any logical statement. Using this, we can succinctly write the above table as AB, A and B, A or B, and then we need this symbol going over here for the not A and not B. Don't know why they didn't add that on. Truth tables are very useful for two reasons. By breaking complex statements into smaller statements, we can gain a better understanding of the complex statement itself. We can easily determine when two statements are equivalent by comparing their truth tables. By knowing the truth values in the third and fourth columns, we can combine A and B with A or B to make a larger statement. A and B and A or B. Okay, what are the values of A, B and C and D, in that order? So 1, 1, so 1, 1, so it's basically 1, 1 added together. So do two ones make a 1? Or do two ones make a 0? Right, here we go. Two ones added together make a 1. Okay, so that's answered that question. So two ones added together make a 1. So the first one is 1. 1 and 1, 1 and 0. Now, does 1 and 0 make a 1? So we've got A and B here, 1 and 0, and that makes a 0. So when it's AND, they need to both be a 1 for the answer to be 1. If only one of them is a 1, you get a 0. But then for this one, the OR, only one of them, only one of them needs to be a 1 to get a 1. Where with the AND, they both need to be a 1 to get a 1. Can't click on it. And then with 0, 0, they're both 0. Okay. Right, so because we've got an AND here, it's 1 triple 0. Happy days. Right, David says he'll come to a party if Alice and Bob are both coming, or if Charlie is not coming. This is shown in the truth table with the output column missing. How many of values? That's a weird phrasing. How many of values in the last columns are true? Okay, right. I might need some paper here. See if I can work it out in my head. Right, A and B. So that's a 1. Or not C. Or not C. So it's a 1 and a 1. So how many are true? So the 1s are true. So that's 1, 2. We've got an OR C here. So that's true. That's 3. So this one is not an OR. In a minute, is it OR is it OR not? David says he'll come if Alice and Bob are both coming, or if Charlie is not coming. Right, so if Charlie is not coming, so if it's a 0, then it's true. If it's a 1, then it's not true. So that is 1, 2, 0, 3, 0, 4, 0, 5. So it's 5. Brilliant. Consider these 3 expressions. Okay. Not A or not B. Not A and B. A and not B. Right, okay. Which of these expressions, if any, are equivalent? Right, I'm grabbing some paper. I can't do this in my head. Right, so not A is a 0, or not B is a 1. So that makes a 1. So number 1 is 1. Not A and B. A and B makes 0 because they both need to be a 1 for the answer to be 1. So not 0 is also a 1. So the top two. So the top two are equivalent. Let's see what the third one is. A and, so 1 and not B, which is 1. So 1 and 1 is 1. They're all 1. What? All the expressions are equivalent. Right, am I working this out wrong? Let's have a look. We haven't got a not chart. We haven't got a not chart to double check. That's frustrating. If they put the not chart up here, we could double check our workings out. I reckon all expressions are equivalent. Oh, 1 and 2. Go on, explain it to me then. So A and not B. So why is this not the same? A and not B. Not B is a 1, A is a 1, so 1 and 1 equals 1. What? Are you trying to tell me that because it's in a bracket, it doesn't count? I don't get it. Why have we not got this equation up here? Right. Not A and B. Not A and B. Not A and B is a 0. So that's a 0 or a 1. In a minute, I'm getting well confused here. What on earth is going on? Oh. Wait a second, no. How is... Right, so A isn't 1 and B 0. That's what I was working out, as if A was 1 and B was 0, but they aren't 1 and 0, they are just representatives of numbers that we don't actually know. So that's where I was working it out wrong, but how is that a 0? So, because it's an OR, how does... So is that negative? That's an OR, but how is this a 0? I don't get that. Right, if it's false or false, then the answer has to be false. Is that what it's saying? Because the way I was looking at it was, it's always true unless you have double false. And because A and B are both negative, you would assume that one of them is true and one of them is false. So you would always have a true. But it's looking like if you have two ORs which are both negative, then it classes as a false. But obviously this is the first time that I've seen this table, so I didn't really know how this worked, this equation. So that equation is actually 0 and not 1, because two falses, regardless of the value, come out as a false. Right, so the next one is negative A and B. Right, A and B is 1, so negative 1. Right, okay. I understand it now, I think. Let's just go back all the way to the top. Right, A, B, so they're just columns. We don't know what the columns represent. Right, I think I get it. Yeah, I get it. Right, if we have a look here, this is the chart that we need to look at. So basically, A and B added together make a 1, regardless of the numbers. So this and this make a true statement, where this and a 0 make a false statement. So we have to always assume that the numbers are 1 for both, I think. That's really confusing, having A and B both as a 1. Right. Maybe we don't have to have it as both a 1. Maybe we have to work out all 4 possibilities of 1, 1, 0, 0. So 1, 1, 1, 0, 0, 1, 0, 0. So maybe we need to have 4 answers for every equation to be able to come up with the actual answer. So that one is 0, 1, 1, 1. And the reason it's 0, 1, 1, 1 is because the equation starts with a negative. If it didn't start with a negative, it would be 1, 0, 0, 0. Okay, so that one's also 0, 1, 1, 1. And the reason that this is 0, 1, 1, 1 is because the opposite of A or the opposite of B. So it's 2 opposites. So the answer is 0 because they're both negative. If they weren't both negative and it was A or B, it would be 1, 1, 1, 0. But because they've got the negatives in there, it's 0, 1, 1, 1. I think that's what it's trying to say. God, this is confusing. And then step 3 is 0, 1, 0, 0. Okay. So what is this? A and negative B. Right. Yes. This chart is actually showing us what negative B is. Negative B is the opposite of B. So it doesn't mean that it's a 0 or a 1. It's only a 0 or a 1. So it's not a 0 or 1 every time. You have to do all 4 of them to get the correct answer, yeah. Okay, I get it now. So it's really long-winded to work these answers out. But we can get there now that I understand the premise of the equation. Right, I understand what truth tables are now. Happy days. So now I should be able to get all the rest of the questions right. It's just going to be a lot of working out. Right, a certain logical expression contains only and or. So a certain logical expression contains only and or symbols. That means there are no not symbols. Okay, without knowing the expression itself, how many rows of the truth table can we fill in correctly? That is, can you decide the expression evaluates to? Can you decide what the expression evaluates to without knowing what the expression is? Right, I think I understand. If we open up this explanation again. No, it's not this one, is it? It's this one here. So basically, we can fill in this. Technically, I think we can even fill in this. But I don't think that's just giving us letters and not numbers. So I reckon we can fill in these. So two parts. We've got ands and we've got ors. Technically, we can fill in the A's and the B's as well, but I don't think that that's what it means. I think it means what can we actually fill in, and then all of these are the things that you add to it to be able to fill these in. So I think the answer is 2 because we haven't got any knots. Brilliant. Let's just show the explanation just to make sure. Yeah, so that's what it's showing us, the ands and the ors. Oh my goodness. What on earth are we looking at here? Right, this is the case even if there are 3 or more inputs. Any combination of all true statements combined with any number of and or statements will be true. And any combination of all false statements combined with any number of and or statements will be false. That means even if you elaborate expression like will be true when all inputs are true and false. When all the inputs when all the inputs are false. Say again. What? That means when you elaborate expression like will be true when all the inputs are true and false when all the inputs are false. Again, this is as long as and or are the only operations used. So, right. I think I understand what it's trying to say. If all of the inputs are 1 on the table, so A, B, let's say you got A, B, C, D, E, F, G. If all of the inputs are 1 and you have an AND symbol in the equation, no matter where the AND symbol is, the answer is always 1. Where if one of them is a 0 and you have an AND in the equation, it doesn't matter what the rest of the equation says, the answer is going to be 0 because the AND will automatically make it false if a single one of them is 0. Oh, and the internet's down. Bear with me. Right, we're back. And then the same will apply with if there's no ANDs and only ORs, then as long as a single one of them is a 1, then all of the answers will be 1. And then it's only if all of the answers are 0 will you get a 0. And then this only works if there are no negative symbols. So I've no idea what will happen if you put negative symbols in. But at least we've worked that out anyway. Right then, looks like we're on to a difficult one next, so I'll see you in the next one. Right, next up, basic logic gates. In the previous lesson we wrote logical expressions in terms of and, or, and not. Computers parse logical expressions in a slightly different format using logic gates for big expressions. These are often easier to understand. The 3 basic logic gates remain the same. Lines feeding into the gate represent inputs, and the line feeding out of the gate represents the output. For example, 3 basic gates are shown below: and, or, and not. Okay. Of course, outputs of one gate can be used as inputs to another. This allows us to represent a chained expression like A and not B, or not A and B as a circuit. A and not B, or B and not A, or, and then the output. Okay, I think I understand it. The diagram below shows AND gates. That takes 2 inputs from the left that each produce 1 output to the right. AND gates will output 1. Right, I feel like I need to write this down. Okay. AND gates will output 1. AND gates output 1 if both inputs are 1. Otherwise, they will output 0. Yeah. You can read 1 as equivalent to true and 0 as equivalent to false. Right, what happens if you have 2 zeros going in? Does that mean it gives a 0? Doesn't tell us. I'd imagine 0 and 0 equals 0, but I don't actually know if that is true, because in this case 0 and 1s are not numbers, they are trues and falses, so false and false might actually equal true. So I think 0 and 0 might also equal 1. What will the output be at the question mark? So 1 and 1 equals 1. 0 and 1 equals 0. Okay, which of the following logical expressions corresponds to the circuit? One, A and B and C. So A and B bracketed and C. A and B bracketed and C. Yeah, A and B. Yeah. Okay. This circuit contains 3 AND gates and 2 OR gates. What's the question mark? So, right. Do I need paper for this? 0 and 1 equals 0. 1 and 1 equals 1. 1 or 0 equals 1. So we got 1 here. 1 and 0 equals 0. 1 and 0, or sorry, 1 or 0 equals 1. Happy days. Nice and easy. What gate goes at the question mark? Right, I need to work backwards. So 1 means that both of these need to be 1, which means that needs to be an OR. Okay. Circuits like logical expressions can be equivalent. For example, the following circuits are equivalent. A or B is the same as A not not. So if you have 2 nots, they cancel each other out. You can just cross them out. We've done that in a previous lesson. Two consecutive NOT gates have no effect. This is especially important for circuits, as we generally want to build circuits that are as small as possible. Right, okay, so that's easy to remember. 2 NOTs can just be crossed out. Which of the following gates will always output true? Oh, God, right. So I'm going to need to do 4. No, in a minute, not 4. We've only got A's. So we just need to do 2 for each one. A 1 and a 0. So if A equals 1, we never found out if 00 equals 1 or 00 equals 0. I'd imagine it equals 0. I think if it's an AND, it's only ever a 1 if both. So it's only ever true if both statements are true. If both statements are false, it's always false. I think that's how it works. It's not like a double negative. I think this is not like that. I think it's, yeah, I don't think it's a double negative. Right. I think this not business is the double negative. And this is just 2 false statements. So 2 wrongs don't make a right. Right, okay, let's see if we can work this out. So gate 1. So if A equals 1, so we got 1, 1, and then the output is 1. If A equals 0, then the output is 0. Okay, so the two answers that you get for gate 1 are 1 or 0. So that means that this AND is going to be false as well, because you can only ever get one true and 3 falses from an AND gate. I think that's what's going on. So one of these two is true. Oh, in a minute, are they just assuming that A is 1? That can't be right. That's not what we did in the last question with the truth tables. Right, in a minute. Yeah, I get it. I know what the answer is. The answer is gate 4. Because if gate 3, if A is 1, 1 and 1, if it's OR, it's AND OR, which means the answer is 1. But if this is 0 and 0 with OR, then the answer is 0, because 0 and or 0 equals 0. Where with this one, it's not, it's the opposite of A. So it's truth and lie, or, and or, I should say. Truth and lie with an or is a truth. And because these two are opposite, no matter which one you change, the opposite will change. So you'll always have one truth and one lie. And because it's an or, it counts as a truth. Got you. Right. Which of the following gates are equivalent? Oh, wow. Okay. I can feel my brain power gradually diminishing. Right. Not A. Not A. Not B. Or means, if you have two knots in an or, that means it's always a knot. I think. We haven't got a table for that, have we? No. Now, I could be wrong about this, but I'm going to guess that if the inputs are knots and they go into an OR, that the answer is going to be 0 like it was in the truth table. So I reckon gate 1 is 0. And then gate 2, A and B is 0 because they need to be the same to get a 1. And then the not, the 0 turns into a 1. So I reckon that gate 2 is a 1. And then gate 3, A and not B is two 1s going into an AND, which makes a 1. And then the same applies here. Oh, wait a second. Do I have to do... I'm going to have to do 0s and 1s for all of these. I need to make a truth table out of it, don't I? I reckon I'm going to need to make a truth table out of this. Oh. Right, let's just assume that... Oh, I don't know. That's a stupid thing to do. You should never assume. I need to make a flaming truth table out of all 3 of these gates to get a proper answer. Right, which one? Right. Let's make a truth table out of each one of these gates. Let's do it properly. Come on now. So, truth table. We have A, we have B. Then we have 1, 1, 1, 0, 0, 1, 0, 0. Then we have a not A and a not B. So for the not A, you would have 0, 0, 0, 1, 1, 0, 1, 1. Then for... Right, what's the next thing I need to do? So I need to do... Let's see if I can put these into an equation, if I can remember how to do that. So it needs to be not A or not B. So not A and not B. Then we end up with... So gate 1 is... Oh, I can't remember what not... How it's not represented in the table. Are the zeros a 1? Because it's a not. No. No, it can't be. So I reckon it's 0, 1, 1, 1. Yeah, I'm 90% sure the table for gate 1 is 0, 1, 1, 1. Then for gate 2... Sorry, I know you can't see all of this writing down. Hopefully my explaining is helping to some degree. Right, so for gate 2, the 4 different possibilities are A1, B1, then A1, B0, then A0, B1, and then A0, B0. So they're the 4 possibilities. So, because it's an AND gate, the only thing that's going to be a 1 is A and B being 1. So it's going to be 1, 0, 0, 0. But the NOT changes all of the answers to 0, 1, 1, 1, which makes it exactly the same. So these two gates, although they look completely different, output the exact same data. So let's see what this one outputs. Right, so we've got A and not B. Right, so the first one, A and not... Wow, that is one heck of an equation. Right, A and not B. Let's do this down here. Sorry, bear with me. Right, so if A and B are both 1, then this makes it 1 and 0, 0 and 1, which makes 2 zeros going into an OR, which makes a 0. Then if A is 1 and B is 0, that makes 1, 1, and then 0, 0, which makes a 1 because it goes into an OR gate. So it's 0, 1. Then it'd be the same for the second one. So it's 0, 1, 1. And then if they're both 0, it'd be 0, 1. No, wait a second. If that is... Yeah, that'd be exactly the same. 0, 1 would give a 1. Right, so this is 0. Yeah, so it's going to be 0, 0, 1, 1, 1. Exact. I think all three of these are exactly the same. I've come up with the same answer on all three of them. Incorrect! Oh, what did I do on this last one that was wrong? Right. Right, this is what I've just drawn out, basically. The first gate is equivalent to... The second gate is equivalent to... The third gate is equivalent to... Comparing the first and second gates, note that the truth tables are equivalent. 0, 1, 1, 1. Yeah, that's what I got for both of them. So how is the third gate different? To find the third gate is not equivalent. Generating the entire truth table isn't necessary. Just consider A equals 0, B equals 0, which for the other two expressions generates a 1. What? I'd rather you have shown me the goddamn truth table, because I don't understand it. Oh, I wish they'd have just shown me the truth table. I don't understand it. I understand all of this. I got these two perfectly fine. I just got gate 3 all messed up. And it's not giving me the damn truth table. Well, that's not helpful at all now, is it? Right, to find the third gate of A and not B, or not A and B, is not equivalent. Generating the entire truth table isn't necessary. Just consider A equals B and A equals 0 and B equals 0, which for the other two expressions generate a 1. So if A equals 0 and B equals 0, that generates a 1. Okay. But on this one it generates a 0. So why does it generate a 0? A and, so A and not B, so 0 and 0. Why have we got an OR here? Why is that an OR symbol? That's an AND symbol. What? Why have we got an OR symbol here when we've got an AND symbol here? So is this OR here meant to be over here? Yeah, because this is the AND symbol for this. So A, 0 and, that's the AND, yeah, 0 and 0, 0 and 0, or 0 and 0 equals... Right, I'm still not understanding this equation. Equals 0 and 1, or 1 and 0. How does that equal 0 though? And why is there another and? Oh, sorry, that's an or, isn't it? Why does this equal 0? They're ands. Why are they ands? So is that saying that this equation is the same as this equation? Is that what's going on here? So 0 and negative 0 is the same as 0 and 1. Yeah, that's what's happening here. They're just changing the format of the equation to show us what it's doing. So 0 and not 0 is the same as 0 and 1. So A and not B. What? No. A and not B is double A. Oh, that's if A and B both equal 0. Yeah, so it's if A and B both equal 0, so it's the fourth line of the truth table. So this equation is the fourth line of the truth table, basically. And the reason that it's false, a 0 at the end, is because right, let me just have a look at this truth table. So this not at the end is changing the 0 to a 1. This or is because you've got two different things here leading into an or, you'll always get 1. No, that doesn't make sense, does it? Yeah, not. Yeah, because the nots, the table is turned upside down. And then for this, A equals B and B equals, sorry, A equals 0 and B equals 0, which for the other two expressions gave 1. Where for this one, it's 1 or 1. Right, 0 and 1 equals 0, or 1 and 0 equals 0, which 0 or 0 equals 0. So what? So how did we get that? What answer did I give? Oh. Somehow I've worked it out as 0. I've worked it out as 1 and 1. In a minute. I have no idea what I've done on my truth table. Anyway, we've spent enough time on this. We've spent enough time on this. This is incredibly complicated. And I got it wrong. So let's move on. Right, logic gates are used by computers to perform all sorts of operations, but designing the circuit can be tricky. Yeah, you're telling me. We'll tackle addition of numbers, which generates many gates, in a later lesson. But for now, let's consider a simpler problem. We would like a machine that takes 3 inputs, A, B, and C, and returns 1, if and only if all inputs are 1. We would like a machine that takes 3 inputs and returns 1, if and only if all inputs are 1. This can be done with 2 logic gates that are identical. What? Well, not is going to give a 0, but I don't understand how or and and are not going to both give a 1. Because if it's 1, if all of the inputs are 1, then the answer is going to be 1, regardless of how many inputs we give. Let's put or. Oh, it is and. I should have trusted my instincts. But I don't understand why or isn't also correct. I mean, I knew it was and. I don't know why I changed my mind. I was just pretty certain that or was also correct. So let's find out why or is not correct. First, we want to check A and B are both 1. This can be done with AND. A and B. Then we want to check that output against C both still need to be using AND. Yeah, okay, I get that. So, it's not explaining to me why OR is wrong. So, yeah, I knew that AND was correct. I just thought OR was correct as well, and it's not explaining why it isn't. I disagree. I disagree. I wonder if we can find a table to explain why I disagree. I bet one of these has got a table. No, there's no OR on this table. Oh yeah, there is. See this OR here? The table is reversed. Basically, just look at the numbers. Right, I should probably find a better table. That's not a good table. That hasn't got a table. That hasn't got a table. That hasn't got a table. God damn it. I can't show you what I'm trying to explain. That's frustrating. But basically, OR is AND/OR. In all of these things that we've done, OR always means AND/OR. So how can AND not, how is OR not working as AND/OR in this particular equation? Because we've got an AND, so we know AND is correct, we worked that out. So why is AND/OR not also correct? Because it's AND/OR. So every time it's an AND, the OR should also apply to the ANDs. So I don't understand why OR is not correct. A binary number is a number. Oh my, what? Okay, I think we've reached our limit. I think this is as far as we go on this course. Oh my god, I'm not doing binary to the power of 10. Are you kidding me? I'm not even going to bother reading it. Alright, suppose you want a machine that takes a binary number with 4 digits, A, B, C, and D, and outputs 1 if the number is even. How many logic gates does this require? I have no idea. I don't even want to try and figure it out. Suppose you want a machine that a binary number with 4 digits that takes a binary number with 4 digits and outputs 1 if the number is even. Right. I have no flaming idea whatsoever. No flaming idea. Right. How many logic gates does this require? I'm going to guess 2. 1, apparently. A binary number is even if and only if the last digit is 0. So only 1 logic gate is required, a single NOT applied to the input D. If that digit is 0, the number is even, so the output will be 1, otherwise the output will be 0. Makes no sense to me. Sorry, you've lost me. We've reached our limit. I might have to skip the rest of these, this section, and hope that the next section goes on to something a little bit more comprehensible. But anyway, I think we'll call it a day for this one. It's been a complete mind blag. And yeah, let me know if you understood any of it, because, well, any of the end bit anyway, because that really confused me, that did. But regardless, still enjoyable. Hope you enjoyed it too. Cheers for watching, take care, and I shall see you soon.